This is a quick look at the PS3 code for the Mini-Skidi running under the Arduino interface. And we're going to look at maybe customizing it for those do-it-yourselfers that have their own hardware that might be different servos, maybe a little bit different N20 motors. Previously, we only had the web interface available. The PS3 uses a new library that's fairly well written. It's called the PS3 controller.h library, and loading it into your Arduino interface is covered in one of the workshops that Professor Boots puts on, so you can join that if you want to look at those details. It's an excellent release in that it creates a full template to allow users to customize the code for using other buttons, other parts of the joystick of the PS3 controller, really easy to follow. And it doesn't need to be modified if you're just following the kits. You've built it up from the kits and are just using sort of the standard build. But if you're a do-it-yourselfer and you've got different servos, or you want to modify the code to use different buttons, you may find that you want to modify this code. So this is just a little walkthrough of how that code works and some easier ways maybe to modify it. Now, first off, all hardware that's based on microcontrollers really doesn't do anything without software. So one of the things that's really a benefit is to get some type of good background in programming. And it's pretty tough to do on an ad hoc basis. I really recommend take a course in C programming. The Arduino interface is really based in C. It's got some object-oriented stuff in it, and there's more and more object-oriented code for microcontrollers. So I also recommend a basic course in Python. That's a fully object-oriented language, and you can learn a lot about objects by studying Python. And either just take a basic course in it, don't go too deep into anything, but C is certainly the most popular and most important, because most new languages are based in it, whether it's Java or C. There's Objective-C, and so many others. So the hardware components often need you to modify code to adapt to hardware characteristics. Every time I put a new servo in, I've got to change the endpoints, or if I'm using a different type of motor, I may need to change some parts of the code. So learning how the code works and knowing how to modify it really is a huge, it sort of opens up the whole DIY stuff for you, and I think you'll get a lot of rewards out of this. So my experience, I don't have a lot of experience with these small microcontrollers like ESP or Arduino Unos, but I did a lot of professional programming years ago. Now this was 30 years ago with microcontrollers, and I used a lot of interrupt-driven routines. And surprisingly, these microcontrollers today are very similar to that. So all the design principles are classic. So it's fairly easy when you get this experience to adapt to most of this new hardware. So let's first start to look at the code and sort of have a little walkthrough about what it does. And before I do this, I might just talk a little bit about the overall structure. So this is the start, and these are the libraries that you need to run the PS3 code. So you need to make sure that these are loaded in your Arduino interface. Now there's three main modules. This PS3 library has a module called Notify. And what that does is it runs, I believe it runs on an interrupt basis, meaning think about your heartbeat. Every time your heart beats, this gets executed and then it stops. Next heartbeat. So this may happen every 10 milliseconds, 1 millisecond. And what it does is it pulls, or it looks at every button on the PS3 controller. And if something happens, it executes some code. The idea in interrupt routines is that these should be small executable bits of code that will execute very quickly. Now, along with this, at the beginning of your code, just like you see here, are a bunch of defines and variable setup, library loads, so just some initialization. Then in the Arduino interface, you have a routine called setup, and that's for code that runs once. So here you set up your motors, pins to be output or input. When you want to initialize maybe your servo to be at a certain position, you would do this once. And then you have a routine called loop. Not interrupt driven. You just put all your code in here and this loops back and forth forever. So these are the 4 modules that are inside this routine. So now we'll take a look at how those work. These define the pins that the ESP has for all these. And if you've wired this in, sometimes it's more difficult to change the wires in a small Mini-Skidi than it is to change the code. If you reverse some wires, you could just put 26 and 25 here. If you reverse the right motor and the left motor, you could put 33, 32 here, 25, 26 here. So you can change or you can modify your code to make up for maybe some miswiring or the wiring that's what you've used in your code. So it's often easier to do it here than it is to actually maybe spend the time to change the wiring. Servo bucket is sort of interesting here. What this does is create actually an object. So here's where object-oriented code becomes important to know. This creates an instance called an instance of a servo object called bucket servo. And class servo does the same thing. And then we can control what we're doing with these 2 objects. These are some initial values of what these should be on boot up. And these are what I call, in classical terms, you'd call these a semaphore, which I don't know how to spell, or basically a flag. It's something that is really up or down like a flag. Semaphore, there was a language of semaphore in the Navy where you had flags that went up and down, and the sailors could send messages back and forth just visually. So these are what I call little flags, and they're true or false. And when this is, for instance, this semaphore is set true, we're going to test it and we're going to move the claw servo up. This semaphore, when true, is going to indicate to the code that the claw should move down. So that's what they're for. Now this is the beginning of the notify routine. And it's really great that it's written this way, but it's not really efficient once you're executing. For instance, you have all these serial print statements, which are really nice because when you're running in the Arduino IDE, these all get displayed on the Arduino IDE. And we have all these tests for every button. So if you want to put code in, this template's here for you and you can just insert your code. One of the problems when you're executing or your final code is that even when you're not in the IDE, it's going to pump this serial line out through the serial interface. Even if the ESP is not connected to anything that can receive the serial code, you're going to do all this processing of writing this code out. You're also going to do all this testing. So this if statement gets executed even though you may not be using that button. However, having it in here in this format is really great for being able to customize your code. Okay, so we have all these routines. We're checking all these buttons to see if they're pressed, and we're sending something out the serial port. Now this is the first thing that we're actually using. This is the analog stick. There's the left and right joystick. We'll maybe bring this over so we can see this code a little bit better. So this is checking to see if the left stick has moved in either the X or the Y direction, and if it has, we're going to get the actual value. Now when a joystick is moved, it's sending an analog value back to the code of -127 or +127. I think if it goes up, it's minus, and I think if it goes left, it's minus, but I could be wrong. But these are the values that these are going to return. And so if the X value is greater than a certain number, then what we're doing is a turn here. We're writing to the right and left motor, low or high, one low high, one high low, and we're likely going to turn left or right. If it's less here, then we're going to turn to the right. Now, notice that we're doing both these tests. If the value is greater than this, we're doing a test, but we're also doing this test. Really, this should be in an else part of the if statement, because if this is true, we really don't want to do that test. There's no point in doing it. We can, it's just a little less efficient. So these are going to cause the motor to turn. Now the Y values are going to cause the motor to turn, to basically go forward or backwards in the same manner. We're going to turn this motor and this motor to make sure that we go in a forward direction, or if the joystick's in the other position, we're going to go in the backwards. And I may have these reversed. This could be the backward, this could be the forward, but basically the motors are going in the same direction. And if we are in this deadband area, which means if we look at our joystick, if we press it all the way up, it's going to be at a 127 or minus 127 value. If we go this way hard, it's going to be 127 or minus 127. But if it's close to the middle, these values are going to be between negative 30 and 30. So what we're saying is if the joystick's in the middle, we basically want to stop our motors. Now there's two ways you can stop motors. If you put both of these inputs low, your motor will coast, which is what you want when the motor is driving wheels. You could actually put both of these high to stop the motors, but this does magnetic braking. And if you put this in, you'll find that when you put your joystick to the middle, it just basically brakes. You really don't want that type of motion here, but it's something that is possible. We'll show where it's used in a second. So that's how the motor controls work. This is the other right joystick, which is used for moving the arm up and down. And you'll notice we do have all kinds of tests that aren't necessarily being used here. We're getting the X value of the right joystick, but code could go in here. We're doing these tests, but we don't have any code in here. We're only using the up and down of the right joystick to move the arm motor up and down. And this code is very similar to the drive code in that we're writing to the arm motor either a high or a low to move it up or move it down. And this right here will stop the arm. Now I prefer for the arm code to use high for both these because this will break the arm motor. What I have found is when my little skiddy has something on the bucket and it's moving it down, if this is fairly heavy, what can happen is that when you coast the motor to stop it, if this is heavy enough, it will drop the motor right down to the bottom. Unless you're using those gears, the extra gears that's available in V3, it may not do it then. But certainly putting these both high, I do that quite often. And it will stop this sort of in its tracks halfway. Now I also use a little slower N20 motor. Mine is about, if you were using a 12 volt motor, I'm using anywhere from a 30 to a 60 RPM motor for the arm, so something a little slower. That's just my implementation, but that's something you can play around with. Now here's where the claw events happen. These are the shoulder buttons, or the buttons where your index finger go. And it's sort of neat what we're doing here. We're actually setting a flag. So if I press a button, I'm indicating, I'm setting this flag that I want to put the servo up. Now, a delay, I don't think this is actually something you want to do inside the notify interrupt routine. We're doing a little delay here, and I think this is just to get the servo so it doesn't respond quite so quickly. But one of the problems in writing code which takes long time to execute inside an interrupt routine is that you're going to fire the interrupt routine, the notify routine. You may come down here and you're going to start a delay. Now this delay is a delay 10 milliseconds. I think at one time it was a little more. And so it's just going to stay here and spin. Meanwhile, if this is too long, this interrupt routine or the notify routine is going to fire again. So you're going to get all these routines which are being nested inside each other. Not a good idea, because in order to keep track of backtracking when everything is done, you need a certain amount of RAM. And if you do too much nesting, you can run out of RAM and your code can crash. So although setting a flag is a really good idea here, as you'll see, doing more code or setting delays in here may not be a good idea. And so when I rewrote it, I took that out. But certainly when a button is pressed that indicates you want the claw server to move up, that's what you do, set the flag there. Now, if once you release the up button, you want to make sure you set that flag false, because you don't want the claw to move up anymore. Now we also have flags to move the servo down along with these delays, which again I might take out. And you have this down, so you have a flag to indicate whether you want to move the servo down the same way as you have up. And you need two flags. You can't just assume that if I don't want to move the claw servo up, I necessarily want to move it down. I may want to stop it. So you've got sort of three things, and you can't do three things with just a single flag. You need two flags here to control that. We do the same because the bucket works the same way. Okay, so this was the claw. We weren't moving the bucket up and down. We were closing or opening the claw. We just used the terms up and down. Here's the bucket, which works the same way. We're setting the flags true or false for whether I want to go down or whether I want to go up. And likely if I press okay, so this one button is for down. This is the button that moves the servo down. And if you just want to change these flags, you would reverse the order of these buttons. But it works exactly the same way. And if you have this set up inside your IDE, every time you press a button, you'll get a little message so you can make sure this is all working properly. Now, this is all code which isn't used here, but it's in there for your purposes. However, I would remove it in a final version just because I don't need to do these tests. I'm not running these buttons. Now also in here, he has some lights code. So if you press the right joystick, you press it down, this event here becomes true. And what we do here, we have a little flag that determines whether, that tracks whether the lights are on or off. So if the lights aren't on, that's what the exclamation point in front, if the lights aren't on, then we're going to turn them on. So this stays low and this goes high. And what that does is it puts 5 volts or 8 volts, your VCC voltage, to your little LEDs that have a resistor. And this is this input. And this is this input. Now, when we want to turn them off, that is, if your lights are not on, we turn them on. If the lights are on, we want to turn them off. We'll come down to the else statement. All we do is set this low. So if this is now grounded here, there's no current that flows through the light. So we really just need to change this aux light 0 from high to low. This one's staying low all the time. In fact, we could just in the setup routine, we could actually take this statement here, put it in the setup routine, and then never change it and just use this statement here. Now here is where we actually do the movement of the claw servo, and this is what I might change. I would take this out of the notify routine and I would put it in the main loop. What happens here is that, and he's using a servo delay. This, I think at one instance, this used to be a value of 4 or 5. So what we have here is that when we come into this routine, we have a little delay, a little counter that counts up. So every time we're in this routine, we're basically incrementing this delay counter. And once it gets to this value, we're actually going to do something. That is, we're actually going to write to the actual servo. So if we reduce this number to 1, our servo should update faster. We're only doing servo write, so we're only updating the servo in these two statements if the servo's beyond this value or less than this value, so between some endpoints. Now when we put numbers in code like this, we call these magic numbers because the reader does not know what these are. So it's probably better, since this number appears here and here, and this number appears here and here, to give these values up in the define way back. So we could define maybe a claw max, say of 170. And then if we use the name here and the name here, we may find that we put a new servo in and, yeah, I don't want that to be 170, I want it to be 160. Well, instead of having to change it in multiple places, I just go up to the top and I just change that here to 160, and my code all takes care of it. Also, by putting names in here, it makes modification easier because the person knows what this means. For instance, this 2 should probably be a servo delay update constant up in the defines as well. So this is what I mean by removing magic numbers. So the bucket movement is done in the same way. And then finally, we're done our notify routine. This is just checking to see if it's connected. This is the setup, which runs right at boot. This runs once. So we're basically setting up our connection. You're making sure that you're inside the PS3 connector. Here's where you have the 6-axis app to write to your PS3 controller to put in some MAC address. And whatever address you put in, you've got to make sure you put the exact same address here. Now make sure that MAC address is not a broadcast address. You can't use, for instance, 00 in the very first bits of the address. So you can also add a statement here if you want. PS3 does, if you find this is not working, you can actually look at the PS3 code, and there you can read the address that's actually being set. So this is supposed to set it. You could then read it back and see if it was actually being set. I don't have the statements right at my fingertips for doing that. So it sets up all the motors to be outputs and the lights to be output. It writes to the bucket servo to give it an initial position, and the claw servo to get an initial position, and these values are defined right at the beginning. And then it writes those to the servo, and then it's done. And from here, it just goes into this loop which executes forever, but really doesn't do anything. It just checks every so often to see if the PS3 controller is still connected. If it's not, it just delays. You could actually take this out if you wanted to. You just do this test more often, but this loop runs forever. So that's how the code works. Now, So we'll come back to how would I modify such code to accommodate a wide range of different hardware or things that you might want to do a little differently. So I would remove the serial print statements in final working versions, and I'm going to show you how you can actually leave those statements in but get them not to compile in final versions, so you can sort of have it both ways. Remove some of the magic numbers to make it a little easier to update your code if you make multiple skiddies and they have different hardware, or to try different things. If you come back to your code in a month or two, then you start to wonder, gee, I wonder what these numbers mean. So reduce code in the notify interrupt routine. That is, don't actually do the claw or bucket movement there. Move it out to a different place, so which we would do in the loop routine. Rewrote some code blocks. You'll notice in the code that there's a lot of blocks that look pretty similar. They almost look identical. So I would try to reduce those into a single code block if possible. And you'll find inside there are all kinds of conditional tests, and you can reduce some of the ones which you're never going to use, or you can nest some of the conditional tests inside. So you might do one conditional test, or you might do the other conditional test, but you're not going to do both of them because both events can't happen at the same time. For instance, you don't want to move your bucket servo up and down at the same time. You want to do one or the other. So if this is false, yes, then you can test to see if I move it down. But if this gets true, I want to move it up. No point in even doing this test here. So in the next part, we'll look at how I modified those. So this code provides a full throttle for the Mini-Skidi, a proportional throttle. That is, as you move your throttle up a little bit, it'll give a little power to the motors. You may or may not want this, but I'll explain how this works so you can maybe modify your code based on this. I've tried to document it quite a bit so that it's easy to modify. I've used this preferences.h for further use. May store values in an e-squared prom, but you don't need this. You can just use these two here. Now, the very first thing I'll do is, you'll notice I don't have any serial print statements. What I have are what are called debug statements. So let me mark on this a little bit. So normally, here's my little pen here, just a sec. So normally, if I wanted to have something come out the port back to the IDE, you would put serial.print, and you would put a value here or some text. Or you would put print ln if you wanted to print a line, then move to the next line, because a serial print will print everything and then on one line. It doesn't do what's called a line feed. But instead, I've used debug, or I've used debug ln. So what's up with that? How does that work? So how that will work is, I have this little routine up here like this. And what this routine does is, every time it sees debug, it will replace it with serial.print if this right here is a 1. So if this is a 1, it'll replace all those debug lins with this. So what I would do if I were connected to the IDE and I wanted all those statements and information back, I'd change this to a 1. Now, once I'm running my code, I've got it all debugged and I don't care about any of that. I'll put this to a 0. So what happens here is this is now false. It comes to the else. And what happens here, sort of neat, is that every debug statement, well, it doesn't get changed to anything. It's basically changed to a null statement. So it basically just takes all those debug statements out. So it means your little Skidi is not constantly sending messages out the serial port when it's running and it's not connected to anything. So this is a little bit of code that makes that a little more efficient. So I've, like before, have defined the pins I'm going to use. Now here's where I've taken out some of the magic numbers and put endpoints. So if you want to change an endpoint, so these were my bucket endpoints, you just need to come up here and say, that's going a little far. I'm going to change that to 160, because you don't want a server, when the servo goes to its full travel, you don't want it to hit the top or the bottom of anything, because it's actually straining. The motor's going to continue to draw power to try to get somewhere it can't get to, and it's going to stall. And when motors stall, they go from 30 milliamps running up to, could be up to as much as an amp, and they're just going to get hot and burn out if you leave it that way for long periods of time. This can happen when you're squeezing. Squeezing foam balls, picking up little foam balls and squeezing them hard, and I burned out a servo very quickly. So here's where I would set the minimum and maximum for the servo I was using for the claws or the bucket. Now, you'll notice that in the other code, there was a servo update of about 2. It was checking to see if the servo update was 2, and it was incrementing it if it wasn't. Because of the way I've moved mine, my servo update is 2000. That gives me a fairly slow movement of my bucket and my claw servos. But if I move this down to 1000 or lower, it will make my servos respond quicker. So I can get quite quick response from my servos. These are the initial values on boot up of where the claw and the bucket should be. You could just use one of these min-maxes if you wanted to. Now this is a little different. I've used what's called a motor array. So this is the actual statement right here that should be uncommented, but I made a wiring mistake in mine. But basically it works this way. I've got, these are the two, let me do it this way. These are the two pins for my right motor. So it's in this order. These are the two pins for the left motor. And these are the two pins for this. And it's in an array. And if you want to change, you've wired it a little differently, all you need to do, if you've taken your right motor and you've reversed the 0 and the 1, you just need to switch these. If you've put the right motor on the left motor branch, all you've got to do is take these two pairs and switch them, and so on. So all you need to do is make your changes up here for your specific wiring, and everything will be taken care of. These are some other values. You'll notice for all my flags, I put FLG just in the front of the name. That's a standard I use to indicate they're a semaphore or a flag that's going to be used. You'll notice you have the one for lights on, this claw servo going up and down as before. And this is my notify routine. Now here I've taken out all tests that I'm not using. So here is my left joystick, the X and Y, which causes the Skidi to go left and right or up and down. And you'll notice that the whole code, this is it, for moving forward and backwards and up and down. So I shouldn't say that. This is for the turning code. So if my X value is between -20 or 20, that joystick is pretty well stopped. And so what I'm doing here is setting a flag to, if I'm less than -20, let me back up here because I was wrong. This means the joystick is pressed in one direction, less than -20, so between -20 and -127, or it's greater than 20. So here the joystick's either pressed this way or this way. So now I'm going to find out which way it's pressed. If it is pressed to the left direction, okay, it is smaller than this value, I'm setting a little flag to say, hey, I want to turn left. Because I'm using proportional, what I'm doing is I'm changing the joystick value to a number between 0 and 255, because that's what the motors use as PWM values if I'm going to give them some analog control. So remember I said the values of the joystick were between -127 plus 127. So I'm taking the absolute value, getting rid of the minus, and I'm just multiplying whatever number comes back by 2 to get a number that's going to go pretty close to 0 to 255. So that's all this statement's doing here. And then I have a routine, and I should show that, that writes to the motors, both motors at once. So if I go down here, we'll see a routine. We'll see a routine right here. And what this does is it takes 4 values and it writes the first 2 to the right motor, does a little delay, let it catch up. And this is in the loop routine. Okay. We'll see that. And then it writes these 2 values to the left motor. This delay may not be necessary, but it was in the original code, so I put it in. I have a little routine here you'll see called blink LEDs. It doesn't do anything. You'll notice it here, but I'm not blinking anything. But if you wanted to use this routine to blink your lights because some event occurred, like you back up or something, you want to blink your lights, you could use this routine, but it's not currently used. But this routine is used. Let's go back to our code here. So what happens, this is the turn code. So if the flag turn left, if this is true, I'm going to call that routine with my right motor is going to have this power value here, which is this number between 0 and 255. So this input's going to have a number. This is going to be low, and the other motor is going to be the reverse of that, which is going to cause it to turn left. Now, else, that is, if I know I've moved the joystick left or right, but I haven't, that if I haven't turned left, I know I should turn right. So now I'm setting the values to turn the motors in a right direction. Now, if it's not, I guess I was right the first time, this is also moving forward and backwards. So if I'm not turning, that if my values are not here, now I'm going to check to see if the joystick is up or down. So now I'm checking the Y value to see if it's either up or down. So if it's beyond the plus 20 to minus 20 values, that means that I've moved the joystick up and down and I want to basically have some movement. So again, I set a little flag to say, well, is the joystick up? Do I want to go forward or not? Well, if it's greater than 20, yeah, I want to go forward. So I find what the power value is, and if this go forward flag is set, which means I've hit the joystick up, I'm setting my values like this to the motor, and that will cause both motors to go in the forward direction. Otherwise, if I know that I've pressed the joystick either up or down, but it's not up, it's got to be down, I want to go backwards. So this is going to go in the backward direction. Now, I've got another else in here. That I get to if none of these things above, that is, if the joystick is just in the middle, it's not up or down, it's not left and right, then I just want to coast all my motors. I basically want to stop. So this is the entire code here for turning left, right, and left, right, and up and down, moving forward or backwards. And should work for you, although you may need to change your motor positions in that motor array. So let's continue on. Some debug statements here. Here is where I write to the arm motor, And basically I'm just doing a digital write here. I'm not doing an analog write. I'm basically just writing to these motors so they're fully on or fully off. And 4 and 5 in that array are where the ARM motors are, ARM motor 0 and 1 pin. So if my right joystick is up, I'm basically putting the motors in a position to raise it, else I'm just putting these down. And notice I did keep the delay in here. I'm surprised. I should have taken that out because I'm still in the notify routine. I said I didn't like delays in here, so I'll have to take those out and see what happens. Because you're writing very quickly just a single value to the servos, you can do this in the notify routine. So here we're one part of this routine here is going to raise it, one part's going to lower it. I could have these reversed. Otherwise, I'm going to stop the arm, and you'll notice here I put both these high instead of low so that I do magnetic braking. You can choose what you want to do. So these are the events which cause the claw flags to get set. And notice that I've taken these delays out. So I'm basically, if you're pressing one of the shoulder buttons to move the claw open or closed, or the bucket up or down, all these buttons are now doing is setting a flag or clearing a flag, setting it true or setting it false. True or false. That's all that happens inside this notify routine. Same with the bucket servo. True or false, no delays. This is for my lights. I have a light bar, and so I'm actually writing to the lights here because it's very quick and there's no delay. So if the lights aren't on, I'm basically just turning, I'm turning a little flag. Oh, again, I misspoke. If the lights aren't on, I'm going to set this flag to true. Oh yes, and I'm writing. Yeah, I'm doing the write right here. So 6 is the aux 0 of the lights. Remember, if you looked at the code from before, the other aux input should always be 0. So in the setup routine, I'm just setting the aux 1 of the lights always 0, and then I'm never modifying it. There's no need to modify it. So this digital write aux lights 1, 0. You really don't need to do this if you've done this once in the setup routine. So I write this to be a high. Otherwise, if the lights are on and I want to turn them off, I just put this low. So that's it. The setup routine is very similar to that before. You notice right here, I'm setting this aux 1 for the lights low because it never needs to change. These are all the motor array pins. They're all set to output. So rather than have 8 statements, I just have a little for loop here that goes through the motor array. You'll notice all those pins, 26, 25, 33, 32, and it sets them all to output one after the other. So it's just a little quicker way of doing it. Now this is the main loop. Here's where I'm actually doing and moving my claw server or my bucket server. So I've moved, this code used to be in the notify, it's now in my loop code. So if my server delay is less than my server update, and notice I have that as a 2000 number. So if it's great, if my delay starts out at 0, it's going to be less. So we're not going to execute this. We're just going to come down. We're just going to come down here. We're just going to come down here to the else statement, and all we're going to do is increment it. So it starts out at 0. It's not greater than my update, so it just increments. So it comes down in this loop code and just keeps incrementing until it gets to 2000, and then it says, okay, I should update my server. So my class server value, if it's less than the maximum, like I can't open, I can only open so far, then I'm going to update my class server value, which is what I'm going to write to my servo. And then I'm going to reset this delay back to 0. And so I've written once. If the person has still held the button, that flag right here will still be set. And I'm going to go through this little test 2,000 times. And on the 2,000th time, it's going to be, this is going to be greater than. So we're going to come down here. I'm going to write to our servo again. So I'm actually able to speed up my server just by reducing this servo update value here. Now, I only check the claw servo down. That's in an else statement here. So if I find this is true and I go in here, I don't even bother doing this because that's in the else statement. I only check to see if the claw servo down flag is set, is if this is false. If this is false, I come down here, see if I should move the claw servo down, which is sort of closed. And if it is, I'm doing the same type of thing here, except I'm checking a different endpoint, the claw minimum, and I'm decrementing values for the claw servo value. The bucket servo works identically to that, okay, except that I have a bucket maximum and a bucket minimum. Using the same servo update value, I was worried, will it get confused between doing the two things? But it doesn't seem to. It doesn't seem to affect it too much. Usually you're changing one or the other, but not both at the same time. So that works identically. And these are the little end routines. So that's my code. You could certainly modify this if you didn't want to do proportional throttle control. This power value here, instead of this value, you just say power equals 255. That's the only change. And then you would basically get the same digital switching. That is, you'll always get full power or no power. That would be the only change that you would need to do there, and then you're not using proportional values at all. So I hope that had some insight. I can post this. I'm not quite sure where to post it. If anyone would want to try it out, they may need to tweak it a bit for their own specific hardware and wiring.